Welcome to AI Paper Podcasts. Today we are unpacking Agentic Code Reasoning by Shubham Magur and Satish Chandra from Meta.
Right, and the core mission of this deep dive today is figuring out can LLM agents explore massive code bases and reason about semantics without actually executing the code?
Which is a massive question, and the paper's breakthrough answer to that is this concept of semi-formal reasoning. Because, unstructured reasoning, like your standard chain of thought prompting.
It basically just lets agents guess.
Exactly. While fully formal verification using languages like lean or cuck, it's just completely impractical for messy real-world repositories.
Yeah, so this paper introduces structured prompting that acts as a strict verifiable certificate. The agent has to explicitly state its premises, trace execution paths, and actually derive formal conclusions.
And the wins are massive here. Across 3 different tasks, accuracy just skyrocketed. On patch equivalence, which is verifying if 2 patches produce identical test outcomes, accuracy hit 93%.
And that is on real-world agent-generated patches using Opus 4.5.
So for the ML engineers and AI researchers listening, here is the immediate, so what for you?
Yeah, it proves LLMs can do meaningful semantic analysis entirely execution-free, which could replace incredibly expensive sandboxing and reinforcement learning training pipelines.
Okay, let's unpack this. Because the gap between how we currently evaluate code and how we could be evaluating it is just fascinating.
It really is. I mean, if you are building an AI coding assistant today or setting up an RL pipeline, you generally have to run the generated code to know if it actually works.
You need a sandbox.
Right, you need a sandbox. And if you want to skip execution to save compute, you might try using things like SWERM.
The software engineering reward model.
Exactly, or tools like Agentic rubrics or Code Judge.
But why are those unstructured reasoning methods failing when the tasks get complex?
Well, it fundamentally comes down to accountability. Unstructured reasoning essentially allows the model to make sweeping claims about code behavior without providing any explicit, traceable justification.
So it's just winging it, basically.
Pretty much. If you ask a standard LLM to evaluate a patch, it might just look at the diff, notice it modifies a particular file, recognize a familiar pattern, and intuitively guess, oh, this looks correct.
It doesn't actually trace the dependencies across the code base.
No, it relies heavily on pattern-matching semantic clues, like variable names. And when you are dealing with complex software engineering tasks spread across thousands of files, intuition just isn't enough. You need proof.
Right. But if intuition isn't enough, why not go all the way to the other extreme? I mean, why not just use formal verification?
The pure math approach.
Yeah. We have tools out there, Lean, Coq, Datalog, that are literally designed to prove code correctness mathematically. Why not just use those?
Because fully formal methods, while mathematically incredible, require you to formalize the language semantics first. Think about what that actually means in practice.
It sounds exhausting.
That's like trying to write a flawless axiomatic mathematical proof for why a massive bowl of spaghetti is tangled. Legacy enterprise code is just too messy for pure math.
You've got arbitrary repositories spanning multiple frameworks.
Undocumented third-party libraries.
Dynamic typing. Weird reflection tricks.
Exactly. It is practically impossible to translate all of that chaos into a strict formal language. The engineering overhead is astronomical. Plus, current LLMs still struggle heavily with the precise syntax and the specific proof tactics those formal systems demand.
So unstructured is too loose, and formal is too strict. Which brings us to the paper's proposed middle ground, semi-formal reasoning.
Right. Instead of building a specialized architecture or a new model, the agent is given a strict, highly structured template in its prompt.
And it forces interprocedural reasoning.
Which changes everything. Because the template requires the agent to document the exact file and line number for every single claim it makes, it can no longer just guess what a function does based on its name.
It actually has to follow the function calls across the code base, jumping from file to file.
It effectively turns the LLM from a passive pattern matcher into an active systematic investigator.
Here's where it gets really interesting. Let's look at the primary task the researchers tested this on, patch equivalence.
The setup there is straightforward. You are given 2 different patches that both claim to fix the exact same bug.
The question is, do they produce the exact same test outcomes? Do they both pass the pass-to-pass tests and fix the fail-to-pass tests?
And they brought up this highly relatable, motivating example from the Django framework, issue Django 13670.
Yes, the 2-digit year format bug.
Right. Fixing formatting specifically for years before 1000 CE. so dealing with 3-digit or 2-digit years.
You have patch 1, which tries to fix it by calling format self.data.year 04D and then slicing the last two characters off.
And then you have patch 2, which uses the modulo operator, essentially doing a string format of 02D on self.data.year 103.
Now, if you give those two patches to a standard unstructured reasoning agent, it fails completely.
It looks at the two patches, does a bit of mental math, and confidently declares them equivalent.
Its logic is basically, okay, let's say the year is 476. Patch 1 formats it to 0476 and takes the last two characters, which is 76.
And patch 2 calculates 476 modulo 100, which is 76, and formats it to a 2-digit string, 76.
They both output 76, therefore they are functionally identical.
And that highlights the exact danger of unstructured reasoning. It sounds completely logical, but the agent made a massive fatal assumption.
It assumed that the word format in patch 1 refers to Python's built-in string format function.
Yes, but when the researchers applied the semi-formal template, the agent actually caught the bug.
Because the template forced the agent to verify the method definitions.
It couldn't just assume what format meant, it had to actively look it up in the repository's scope.
Let's pause on that, because the mechanics of how it caught this are fascinating. In standard Python, if you type format, sure, the model assumes you mean the built-in tool.
But because of this strict template, the agent looked around the local files and realized, wait, in this specific Django file, there's a custom function also called format that does something entirely different.
Looking at the notes here, it found a module-level function called format inside dateformat.py at line 340.
And this local function does not take an integer. It expects a datetime object.
Exactly the distinction that matters.
Because of how Python resolves names, it checks the local scope first, then the module scope, and only then does it fall back to the built-ins.
So patch 1 ends up calling that module-level function, not the built-in one.
Right. It passes the integer 476 into a function strictly expecting a datetime object. This immediately results in an attribute error.
Because integers don't have a .day attribute, which the custom function tries to access.
So patch 1 actually crashes the program, while patch 2 works perfectly.
The semi-formal certificate forces the agent to trace that exact scope resolution path and explicitly prove why the two patches diverge.
And the results on their curated dataset really reflect the power of that tracing. Accuracy jumped from 78.2% with standard reasoning to 88.8% with semi-formal reasoning.
And to connect this back to the broader picture for the AI researcher audience.
Yes, think about how you currently evaluate agent-generated patches. When they tested this approach on real-world patches using Opus 4.5, it achieved 93% accuracy.
Wait, 93%? How is that even possible without executing the code? If I'm an ML engineer using Python's difflib, what am I getting?
With a strict text diff tool, you'd max out around 73% accuracy. Even using a standard single LLM call, just asking, are these the same? You only get to about 86%.
So hitting 93% without running a single line of code is a massive leap.
It really is. If you are training coding agents using RL, your biggest bottleneck is the reward signal. You usually need a continuous integration system or a secure sandbox to execute the code.
Which is slow and expensive.
Very. This research proves you can generate highly reliable reward signals statically, using the LLM itself as the evaluator, provided you force it to show its work.
It completely changes the economics of training coding agents.
Okay.
So it can verify if a patch works, but verifying a fix is entirely different from finding a needle in a haystack in the first place.
Sure.
If we just give it a broken test and no stack trace, does this structured approach still hold up?
That brings us to the second task, fault localization using the defects4j dataset.
And fault localization is notoriously difficult for LLMs. The agent is given a failing Java test. That is it.
No stack traces, no error messages.
Just the test code and the entire repository. So to tackle this, the researchers used a very rigid 4-phase semi-formal template. Walk us through those phases.
Phase 1 is test semantics analysis. The agent must document exactly what the test does and what its explicit assertions are.
Phase 2 is code path tracing.
Right, building a chronological call sequence from the test into the production code, documenting every file and line number.
Phase 3 is divergence analysis.
Identifying exactly where the implementation contradicts the test's documented expectations. And finally, Phase 4 requires ranked predictions,
where every single prediction must cite a specific claim generated in the previous 3 phases.
It's intense but necessary.
I want to look at the specific case study they highlighted for this. Mockito 8.
Mockito is a popular mocking framework for Java.
And the bug they tested causes a Stack Overflow due to infinite recursion when Java is trying to resolve generic types.
This bug is the perfect illustration of symptom versus root cause, which is where LLMs usually fail.
In standard reasoning mode, the agent looks at the code, sees a method called getActualTypeArgumentFor at line 181.
It realizes this method has no cycle detection and recurses endlessly, and it confidently declares, aha, there's the bug. Add cycle detection here.
It stops at the crash site.
But the crash site isn't the root cause.
It's just where the car finally hit the wall, not where the steering wheel broke.
Exactly. When the agent uses the semi-formal reasoning template, it can't just stop at the first thing that looks broken.
It traces the execution pipeline from the start, generating 10 distinct formal observations.
Testing multiple hypotheses about how different generic types map to each other in this specific instance.
And through that rigorous tracing, it finds the actual root cause way upstream at line 80.
In a method called register type variableson, it discovers an issue with self-referential types.
Imagine a dictionary that defines a word by simply pointing back to the exact same word.
If you try to look it up, you'll just flip pages back and forth forever. That's essentially what happened here in the Java code.
The code accidentally overwrites a safe, bounded type mapping with a self-referential one, mapping the type T to T.
That overwrite is what eventually causes the infinite loop downstream.
So the template forces the agent to do a differential analysis, testing edge cases until it proves why that specific overwrite way up at line 80 is the only logical culprit.
Yes, and the performance bump reflects the depth of that analysis. On the defects4j benchmark, semi-formal reasoning improved top 5 accuracy by 5 to 12 percentage points.
The best overall configuration they tested was Agentic exploration utilizing the semi-formal template, which hit 88.4% top 5 accuracy on the any metric.
Meaning it found at least one buggy hunk of code in its top 5 predictions nearly 90% of the time. The template acts as a cognitive forcing function.
A cognitive forcing function?
It prevents the LLM from getting lazy. LLMs are highly prone to jumping to conclusions based on semantic clues instead of syntactic reality.
By forcing the agent to exhaustively document the execution trace before it generates a conclusion, you bypass that lazy heuristic.
Exactly.
Which brings us to the final task, code question answering using the Rubber Duck Bench dataset.
These aren't just find the bug prompts. These are nuanced questions about complex code bases, evaluated by expert rubrics and LLM graders.
For this task, the template shifts slightly. It requires function trace tables, data flow analysis, and semantic properties.
But the most crucial addition is a mandatory alternative hypothesis check.
The agent must explicitly ask itself, if the opposite of my conclusion were true, what evidence would exist in the codebase?
And then it has to actively go search the repository for that evidence to refute it. It's a powerful debugging technique.
They highlighted a really cool success case in C++R labeled CPP3.
The question asked if there was a difference between using the ACNet method versus using the standard bracket operator when accessing a specific map.
Unstructured reasoning got penalized heavily here because it made a very common assumption.
It correctly noted the const correctness aspect. The @edge a key can be used on const maps while brackets cannot.
But then it went further and assumed that invalid keys were a possibility in this specific codebase, praising for error handling.
But the semi-formal template forced the agent to trace the map's initialization.
It proved that invalid keys are literally impossible in this context because only specific enum values are ever assigned to that map.
It proved an invariant property of the code.
This raises an important question, though. Does this structured reasoning always work? I mean, why does it still fail sometimes?
The error analysis section in the paper is critical here. Look at the Python failure case, Py5.
The question was simple. Do we need this? If not, build directory check.
The agent thoroughly traced 5 different functions, tracked the data flow, and found a legitimate edge case where the directory variable could end up being an empty string.
So it confidently declared, yes, the check is needed, but it was wrong.
Confidently wrong. It built a highly plausible, elaborate chain of logic, but it stopped tracing just one step too early.
It completely missed that a downstream constructor actually triggered a corpus pruning exception if the directory was empty.
Meaning the program would safely cache the error and handle it later anyway, so that original check wasn't needed.
It's like building a beautiful bridge that stops 10 feet short of the other side. Deeper reasoning can sometimes lead to highly confident, elaborate wrong answers if the agent stops before verifying all downstream paths.
And the paper noted a very interesting nuance about the underlying models required for this.
Right. When they used Opus 4.5, accuracy on this QA task jumped from 78.3% to 87.0%.
But when they swapped to Sonnet 4.5, the performance showed no real gain, plateauing around 84.8%.
Implying the benefit of structured reasoning depends heavily on the base model's capabilities.
If the base model doesn't have the intrinsic ability to hold on to complex logical constraints over a very long context window, the template won't magically save it.
You need a highly capable frontier model. So what does this all mean for the listener?
Historically, rigorous code analysis meant building specialized, inflexible static analysis algorithms, custom parsers, taint tracking rules.
A massive barrier to entry. But this paper proves we don't have to do that anymore. We can prompt LLM agents with task-specific reasoning templates that generalize across languages to get near execution-level reliability.
Reducing compute and RL pipelines, enhancing automated code review, and improving static program analysis without needing a team of PhDs to write a custom analyzer.
It's incredible, but it leaves me with a final provocative thought drawn from the paper's future work. Right now, we are spending extra compute on long, multi-step prompt templates to enforce the semi-formal certificate at inference time.
It takes longer and costs more per query.
But what if we used post-training to fine-tune models to internalize this semi-formal structure natively?
Take all these successful reasoning traces and bake them into the model.
Could the models of tomorrow produce these rigorous, traceable proofs of code semantics instantly, without the prompt overhead at all?
Just inherently knowing to check local scope before built-ins.
Exactly. Something for you to think about as you build your next coding agent. Thanks for joining us for this deep dive into the research.
See you next time.